By the end of this video and playlist, I promise you, you are not just going to solve integration, you will own integration. Let's see what we are covering in this video. Let's get started on the concept development of your chapter integration. The concept, the way it starts is from your chapter derivatives, which you have already studied. Now, let me take an example. Let's say we know d by dx of sine x, or derivative of sine x with respect to x. We know this is cos x. Now, integration is also called as antiderivative. Integration is also called as antiderivative, which means it is the reverse of derivative. For example, if your derivative of sine x with respect to x is cos x, that implies that integration of cos x, this is the sign of integral, integration of cos x with respect to x. In derivative, we divide by dx to say this is with respect to x. In integral, we multiply that dx to say that we are integrating with respect to x. Integral of cos x with respect to x is sin x. It's exact opposite of derivatives. If derivative of sin x is cos x, integral of cos x dx is sin x. All right, let's take a couple more examples. We know derivative of sec x is sec x times tan x. This means integral of, so it's reverse. So integral of this sec x tan x, integral of sec x tan x with respect to x is equal to sec x. It's exact opposite of derivative. All right, there is one important thing that we note here. Let's again take the example of sin x. Let's say if I take derivative of, instead of sin x, I take sin x plus 10. What is derivative of sin x plus 10? So derivative of sin x plus 10 is cos x plus the derivative of 10, which is 0, which is also cos x. Now let's see if we take derivative of sin x plus 30. This will also be cos x. Derivative of sin x is cos x plus derivative of 30 is 0. In other words, I'm coming to a point that no matter what the constant term here is in the derivative of that is always going to be 0. This means that if you had derivative of sin x plus a constant, instead of 10, 30, let's say if you have a constant c, the derivative of this is going to be cos x plus 0, which is the derivative of this constant, which is cos x. Now this would imply that integral of cos x is not just sin x. Integral of cos x can be sin x plus 10. Integral of cos x can be sin x plus 30. In generally, integral of cos x is sin x plus that constant c. Now that constant c can take any value. It can take 10, 20, 30. It may be 0. But generally, if you want to say integral of cos x with respect to x is sin x. So integral of this cos x, or this cos x, is sin x plus the constant c. All right, now let's get started with the formula development of this chapter integration. One formula we already understood, that integration of cos x with respect to x is sin x plus c. Now remember to always add that constant c. Technically or mathematically, this c is called as arbitrary constant. Arbitrary constant. So whenever you're done integrating any function, always remember to add that arbitrary constant in the end. Okay, now let's try to develop the full list of formulas that we'll need to solve all the integrals in this chapter. We'll start with the basic formulas. Then there are some specialized formulas that we'll discuss in the further videos, but we'll develop a basic list of formulas first. We'll create a table. Let's say on the left side, I have f of x. On the right side, I have integral of f of x with respect to x. And let's write the constant c. Okay, we already know one formula, which is cos x. Integral of cos x is sin x. I just wrote constant c once so that I don't have to write again and again when I write all the formulas. Integration of sin x. Let's create a table here first. Okay. Integration of sin x is minus cos x. Integration of tan x. Let's complete all the trigonometry first, then we'll move to algebraic, then we'll move to exponential. We know cos x is sin x. Remember sin x, the integration of sin x is minus cos x. Integration of tan x is log mod sec x. It's log modulus of sec x. Whenever there is log in it, basically we always put modulus just to show that there cannot be a negative number inside of a log, because log of negative is not defined. Okay, so we always make sure to not have a negative number inside of a log, which is why that's the reason that we put modulus whenever there is log, basically. Then there is integration of sec x, which is log of, again when there is log we put modulus, sec x plus tan x. All right, now let's look at cosec x. The integral of cosec x is log mod cosec x minus cot x. Okay. Now the integration of sec square x is tan x. Now this comes from, we know that derivative of tan x is sec square x, which is why the integration of sec square x is tan x. Integration of cosec square x is minus cot x. Again, the same logic. The derivative of cot x is minus cosec square x, which is why the integration of cosec square x is minus cot x. There are a couple more. Integration of sec x tan x. Now, whose derivative is this? You know the derivative of sec x is sec x tan x, which is why the integral of sec x tan x is sec x. Similarly, we know for cosec x cot x, we know the derivative of cosec x is minus cosec x cot x, which is why the integration of cosec x cot x is minus cosec x. All right, now let's move on to algebraic functions. Let's move on to algebraic functions. Now, algebraic functions are the functions which look like variable to the power constant. Variable to the power constant. So if you want to write it mathematically, this would be something like x to the power n, which is variable x to the power constant. Now the integration of this type of function, which is algebraic x to the power n, is given by x to the power n plus 1 divided by n plus 1. So you increase the power by 1 and divide by the same power. Okay, let's take a few examples to understand. I'll also tell why I specifically mentioned this differentiation like variable to the power constant. We'll see why is that. But let's take a few examples first here. So let's say if it was x to the power 2. The integration of x to the power 2 is x to the power 3 divide by 3. So you increase the power by 1 and divide by the same power. Let's see x to the power 4. This would be x to the power 5 divide by 5. So you take that, increase that power by 1 and divide by the same power. Let's take a few other examples. Let's take x to the power 100. This would be x to the power 101 divided by 101, and so on. Let's take a few standard ones like square root of x. We know that square root of x can be written as x to the power 1 by 2. Now, we can apply the same logic here. We can just increase that power by 1, or say x to the power 1 by 2 plus 1 divide by 1 by 2 plus 1. So basically just increase that power by 1 and divide by the same power, which is, so 1 by 2 plus 1 is 3 by 2 divided by 3 by 2. Okay, so integration of square root of x is x to the power 3 by 2 divided by 3 by 2. Let's take another standard example, which is 1 upon square root of x. Now, integration of 1 upon square root of x, this 1 upon square root of x can be written as x to the power minus half, correct? By the law of indices, this 1 upon square root of x can be written as x to the power minus half. Now, same logic can be applied. You can just increase that power by 1. So, x to the power minus half plus 1 divided by minus half plus 1, which is equal to, so in the numerator you have 1 minus half, or minus half plus 1, which is half, divide by half, because 1 minus half is basically half. Now you can simplify this further, because we know x to the power half is nothing but root x, and this 1 divided by 2 in the denominator can be taken in the numerator. So this 2 can be taken in the numerator because it's in division. So it will be 2 square root of x. Okay, so this is a standard result that for 1 over square root of x, the integration is 2 square root of x. Okay, let's take one or two more examples. Let's say if the function was 1 upon x squared. If it is 1 upon x squared, now we know 1 upon x squared can be written as x to the power minus 2. Now using the same logic, this can be written as x to the power minus 2 plus 1 divided by minus 2 plus 1. So you increase the power by 1 and divide by the same power. This will be x to the power minus 1, minus 2 plus 1 is minus 1, divide by minus 1. Okay, now this can be written as, so this minus can be taken in the numerator, so minus 1 divide by, so x to the power minus 1 is nothing but 1 over x, because x to the power minus 1 is nothing but 1 over x. So this x to the power minus 1, we could write this 1 over x, and this negative part we can just take out. Okay, I hope that makes sense. So the integration of 1 over x squared is minus 1 over x. Now there is one exception that comes here. Let's look at the exception of this rule, or exception where this cannot be applied. So let's say if your function was 1 over x. If your function was 1 over x, now you know 1 over x can be written as x to the power minus 1. If you try to apply this same logic, let's see what you get. You will get x to the power minus 1 plus 1 divided by minus 1 plus 1. So that would be x to the power 0 divided by 0. Now we know anything divided by 0 is not defined, right? So we cannot write this. So basically this logic cannot be applied in the case of 1 over x. Okay, so for 1 over x, we don't write it as x to the power minus 1. That's the only exception that we have. For 1 over x, the integration of 1 over x is log mod x. Now we know that this also comes from the derivative of log x. The derivative of log x is 1 over x. Okay, so that's one of the reasons that for 1 over x, there is an exception that you don't apply this rule of algebraic functions. for 1 over x, the integration of 1 over x is log mod x. Okay, I hope makes sense. All right, now let's move on to exponential. Remember that when we discussed algebraic, I specifically mentioned that algebraic is something which is variable to the power constant. Okay, algebraic is variable to the power constant. Exponential is constant to the power of variable. It's reverse. Okay, let's see. So exponential, let's look at exponential functions. The way exponential functions are, it's constant. The way you will make out that it's an exponential function is there will be a constant and there will be a variable in the power. So constant to the power variable. If we want to write it mathematically, this will be something like n to the power x, or constant to the power x. In some textbooks, or like NCERT textbooks, they also write it as a to the power x, where a is a constant. Here I say n to the power x, where n is the constant. Okay, so n to the power x, or you can say a to the power x, doesn't matter a lot. Okay, let's actually be consistent with your NCERT, and let's say it's maybe a to the power x. Okay, so that constant is a and power is x, which is exponential function. Now the integration of a to the power x is a to the power x divided by log a. Okay, a to the power x divided by log a. Remember that in derivative of a to the power x, it is a to the power x multiplied by log a. In integration, it is a to the power x divided by log a. Okay, in integration, you divide instead of multiplying. Let's take few examples. Let's say if you have 10 to the power x, the integration of 10 to the power x is 10 to the power x divided by log 10. Also, one thing to note, the base of this log, if I'm not mentioning anything, it is e. Okay, even here, the base, if I don't write anything, the base is e. Okay, so that would mean, if let's say if I had e to the power x, the integration of e to the power x, it will be e to the power x divided by log e. Now, since the base is not, I don't specify the base is e really. Now we know log e to the base e is 1, right? So this will just be e to the power x divided by 1. By rules of logarithm, we know this is the value of this is nothing but 1, right? So this will just be e to the power x. So that implies that the integration of e to the power x is e to the power x. All right, that does cover all the basic formulas that we need to solve most of your NCERT textbook problems. There are still some special integral formulas that we'll look in the later videos when we need them. But for now, that does cover most of the part that we need. Okay, before we move further, there is a special note which I would like to highlight, and it's a very important note to keep in mind. Let's look at the note. I'll explain the note with the help of an example. Let's say integration of cos x dx is sine x. We know this, right? Plus c. We know this already, that integral of cos x dx is sine x plus c. Let's say instead of x, let's say you don't have x here. Let's say if you have, instead of x, linear function of x. Instead of x, if you have linear function of x. So instead of x, if you have a linear function of x, that would become something like integration of cos of, the linear function is given by ax plus b dx. So let's say if you don't have x, instead of x, you have a linear function, ax plus b. Note that power is still 1. This is x to the power 1. This is also x to the power 1. The only difference is there is that extra terms a and b in the way ax plus b. Okay, the integral still remains same, sine ax plus b. The way it was for cos x, it was sine x. For cos ax plus b, it is sine ax plus b, but there is a small difference. You divide by the coefficient of x. Coefficient of x is a, So you divide by a. It's a very, very important thing to keep in mind, okay? Let's take a few examples. This is example number one. Let's say example number two. We know that integration of x squared dx is x cubed divided by 3 plus c. Okay, we know this already. Now, instead of this x, let's say we have a linear function of x. Let's say we have linear function of x. So if instead of x, you have that linear function of x, your function would become, instead of x, we can write ax plus b the whole squared dx. Okay, the only difference is instead of x, we wrote ax plus b. We kept the square the way it is. Now, if instead of x, it was like this, the logic still applies. The increase the power by 1 and divide by 3, the logic still applies. Ax plus b ax plus b to the power 3 divide by 3. Okay, the logic still applies. The only thing is you add that coefficient of x, or from here, you add that coefficient of x, which is a, in the denominator. So basically you divide by that coefficient of x. Okay, let's take an example. So let's say if it was 2x plus 5 the whole square dx. Okay, so this is still like x to the power 2, right? So the same logic applies. You can still say the integration of this is 2x plus 5 to the power 3 divide by 3, but there is an extra term which is the coefficient of x that goes in the denominator, which is 2. Okay, so that there is a term extra in the denominator always. So the integration of this will become 2x plus 5 cube divide by 6. All right, that does cover everything that we needed for concept development of this chapter. If you have any questions at all, as always, please feel free to post comments. You'll also see my email in the description. Feel free to shoot me an email, reach out to me. I'm more than happy to help you guys. Okay, in the next video of this playlist, we are going to solve your exercise 7.1 from your NCERT textbook. We'll solve each and every problem of your each and every exercise. We'll start with, in the next video, 7.1. Then in the further videos of this playlist, you will see 7.2, 7.3. We'll solve each and every problem. So I just don't want to leave any doubt in your minds. So we'll just solve everything in this class itself so that there is no confusion at all. All right. Thank you so much for listening to me. I'll see you guys in the next video.